Let's see a couple of examples of application of this fetish series that we have and how we can solve some simple examples and some more demanding examples. So let's say we want to find the expression in power series of this function here, and we will use our fetish geometric series x to power n, because we know it's convergent on interval -1, 1, and we know its sum also. So what we know is that 1 over 1 minus x is equal to the sum of x to power n starting from 0. How do we write this in a way that we can exploit this result that we already know? So the 2 is not an issue. We'll multiply everything by 2, so that's not a problem. So here we have 3 minus x. We know 1 minus x. So basically what we will do, we'll factor 3, and then we will get something that is closer to what we know. So downstairs we factor 3, we have 1 minus x over 3. So now we have 2 over 3, that's a constant that will multiply everything, it's fine. And then we have 1 over 1 minus x over 3. Now it's easier. We will replace in our fetish series x by x over 3. So that's what it tells us. So 2 over 3 is the constant that we carry in front. And we know that our fetish series is this here with x to power n. And interval convergence -1, 1. Now what we do here to get what our function is, the expression of the function, we need to replace x by x over 3. So let's just replace x by x over 3 in the expression of the sum here, and in the expression of the general term, so x replaced by x over 3, and in the expression of the interval convergence. Instead of x, we have x over 3. So now here the interval convergence will be absolute value of x smaller than 3, so interval is between -3 and 3, open. So you see, we need to be careful to replace x by our expression x over 3 in 3 different places. Here with the sum, here as a general term of the series, and in the expression for the interval of convergence. Super important. So we have 2 over 3, that's a constant, stays in front of the series. So x over 3, so we can write x to power n divided by 3 to power n. So now we could also, we have 3 and 3 downstairs, we can rewrite it as 2 times sum of x to power n, 3 to power n plus 1. We could, we don't have to, it's fine, whatever. And the important thing is really here to have x over 3 in absolute value smaller than 1. Rewrite this properly. So this is absolute value of x smaller than 3. So the radius of convergence is 3, and the interval is open -3, 3. So you see our fetish series was converging on -1, 1, and our new series is convergent on -3, 3. Here the radius of convergence is 3. In the case of the fetish series, radius of convergence was 1. So it's really important to write this part also, otherwise we have a serious problem. Just an observation. So what we can say is that our expression that was given, our function, is equal to this series on interval -3, 3. Now what happens at the end points, quickly? If I put x equal 3, the function is not defined. So the equality obviously doesn't hold, because the function is not defined, regardless of what's happening with the series. Now what happens at x equal -3? The function, if I replace x by -3, I'll have 3 minus 3, so I'll have 3 plus 3 downstairs. So 2 over 6 is 1 over 3, so that's defined. However, what's happening with the series at -3? I'll have -1 to power n times 3 to power n. So 3 to power n will simplify. Here I'll have general term of the series, -1 to power n, which is not going to 0 as n goes to infinity. Therefore, by divergence test, it would be divergent. So even though at negative 3, the function is defined, the series is divergent, therefore the equality is not holding at the end point. At 3, the function is not defined, so equality is not holding. At minus 3, the series is divergent, so the equality doesn't hold. So really, the interval of convergence is open minus 3, 3. Another example, similar to the previous one. Here, the 4 is not a problem, we'll multiply everything by 4 anyways. Again, here we have 3 plus 2x. If we had 1 plus 2x, it would be easier. So what do? We factor 3. So factoring 3, I'll have 1 plus 2x over 3. I'm writing plus as minus minus. So just to resemble more to our fetish series, that's all. So now I have 4 over 3 as a factor in front, that's a constant, and 1 minus this expression here. So now I will take my fetish series and replace x by minus 2x over 3. So that will be the goal. So 4 over 3 is multiplying everything, it's fine, so I multiply it in front, it's not an issue. Doesn't change anything in life, just need to keep it there. So in my fetish series, I need to replace x by negative 2x over 3. In the general term, I need to replace x by negative 2x over 3. And in the expression of the interval of convergence, I need to replace x by negative 2x over 3. This is super important, because now if I rewrite it, this will be absolute value 2x smaller than 3, so absolute value x smaller than 3 over 2, right? So interval is negative 3 over 2 and positive 3 over 2, radius is 3 over 2. Very important. So now it's pretty much over. We can rewrite this with minus 1 to power n, 2 to power n, x to power n divided by 3 to power n. Now here, since 4 is 2 to power 2, we could bring it here. So we'll have 2 to power n plus 2, and then downstairs I have 3 to power n times 3, so 3 to power n plus 1. So I could rewrite it this way. I don't have to, but since it's easy, it's okay. So my expression, my function, is equal to this alternating series here, the power series, and interval of convergence is minus 3 over 2 and 3 over 2. Again, we could plug the end points. At negative 3 over 2, the function is not defined, so there is no equality. Positive 3 over 2, if I plug it here, I'll find out again that my series is divergent. So this is another example of rewriting. So we never get scared by what is upstairs, because we will multiply by this expression, x squared, everything, the series that we get, so it doesn't matter really. What matters is to rewrite the downstairs properly. So again, if I have 1 plus an expression, I know what to do. If I have 1 minus an expression, I know what to do. Here I have 16 plus x4. So I'll factor 16 obviously. So I have 16 factor of 1 plus x to power 4 divided by 16. Now 16 is 2 to power 4, fortunately. So plus, I replace it as minus minus. By the way, you can do this, or just remember that the series with plus is alternating version of our fetish series. It's up to you which part you take. I prefer doing it by the book just to make sure that everything is fine, but you could go faster also. So we have a factor x squared over 16 in front of everything. So this part here, we know what to do. We will replace in our fetish series x by negative x over 2 everything to power 4. Okay, so essentially x to power 4 over 16. So the expression in front times 1 minus x. So this is just to illustrate how we replace in our fetish series. So x is replaced by negative x over 2 to power 4. So it's replaced here. Ugly, okay, fine, but just to make sure that everything fits nicely. And then here it's replaced also negative x over 2 to power 4, everything to power n. And then also it's replaced here in the expression of the interval of convergence. So x is replaced by negative x over 2 to power 4. So obviously this will be simplified a little bit, so we'll have at the end x over 2 in absolute value smaller than 1, so x in absolute value smaller than 2, so the radius is 2 and the interval is open negative 2, 2. So that's pretty much it. We just can rewrite this a little bit. So we have minus 1 to power n, so minus 1 to power n, then x to power 4n, and then 2 to power 4n. So 2 to power 4 is 16, so 16 to power n. Now what we realize is that downstairs we have another 16 from the multiplication, so it will be 16 to power n plus 1, fine. And upstairs we have x to power 4n, and everything is multiplied by x squared each term, so it is x to power 4n times x to power 2, so x to power 4n plus 2. This is just more compact and proper way to write it. So basically that's what we have. If we try to evaluate at the end points, the function is defined in both of them, that's fine, but the series, we can see that the series has the term that is not going to 0. This is another expression. Again, what is upstairs is not an issue. Downstairs we have 1 plus 2x squared, so we know what to do when we have 1 minus, so 1 plus 2x squared is 1 minus minus, right? So now this is cute. We know that we will use our fetish series and replace x by negative 2x squared. So we have x times this. So that's our x times the expression. Looks like this. So basically now we are replacing here x by negative 2x squared. Right, x stays here, right? I replace x by negative 2x squared. This x I replace by negative 2x squared, because x is multiplying the entire series, right? And most important part not to forget is x needs to be replaced by negative 2x squared. So here we will have 2x squared in absolute value smaller than 1, so x squared smaller than 1 over 2, so x is smaller than, in absolute value, than the radical of 1 over 2. So that's important. So we know that this expression is actually our original f, so that's not a mystery. So basically now we multiply x inside everything, so the sign stays as is, it's not affected. X is just changing the power for this expression, so x to n times x, it will be x to n plus 1. And again, you see the interval of convergence is different here from our original case. So it's always important to replace the expression of x everywhere in the sum, in the general term, and in the expression for the interval of convergence. This is a little bit curious as an example. So there are two ways to do this. Either we can split this as x over x plus 2 minus 1 over x plus 2, or we can rewrite it this way, maybe it's faster, because then in that case, in the first case, we would need to add two series. That's a little bit annoying. So basically here I try to have x plus 2 upstairs plus some number. So x minus 1 plus 3, that will give me x plus 2. So I add 0, right? Plus 3 minus 3. So that will give me x plus 2 minus 3 upstairs. So I'll have x plus 2 divided by x plus 2 is 1, minus 3 divided by x plus 2. So now again I need to factor 2 in order to have 1 plus something. So I rewrite it as 1 minus minus. Again, I use the original version of the fetish series When you have plus, you might use the alternating version also. If you want to go faster, it's fine. So we have 1 minus, so our expression is 1 minus 3 over 2, and this expression. So to get this expression, we know that this is equal to a series that will be multiplied by 3 over 2, so 1 minus the thing. So 1 minus 3 over 2 times this expression. So in this expression, we replace x by negative x over 2. We replace it here, so that way we get our function, the expression of the function. Then 1 minus 3 over 2 times, we replace it as a general term of the series. So instead of x, we have negative x over 2. And then instead of x in the interval of convergence, we replace it by negative x over 2. So this will be absolute value of x over 2 smaller than 1, so absolute value of x smaller than 2. So x is between negative 2 and 2, radius is 2. Okay, so basically that's what we have. We can keep it this way or try to simplify a little bit, rewrite. I tried here something, it didn't really change much, so you could actually keep it as is here, it doesn't matter. So you see, in this case we tried to simplify our things by rewriting x minus 1 as x plus 2 plus some number, essentially, or minus some number. Here, though, what we have is an expression, and we use partial fractions to rewrite it. So now looking at this, it seems simple because we have something that is very close to our fetish series, and this is also close to our fetish series. So we will have one series plus another series for this. So let's see how it works. So our f is here, what is known is 1 over 1 minus x. So I just rewrite here, I factor negative 1. So I factor negative 1 here. So I have a minus 1 here. So it will be 1 minus x when I rewrite it. So now it's cute. This is minus 1 times my fetish series. And here again I factor minus 1, so I'll have minus 1 upstairs and 3 minus x. So then I'll factor 3 and I have something like this. So basically I'll have minus 1 times my fetish series, and then minus 1 over 3, and here it will be my fetish series with x replaced by x over 3. And then I will add both of them. So we will see a little bit how that works. So the first part is minus 1 times my fetish series, so there's nothing special. I just keep it as is here. Interval of convergence is minus 1, 1, doesn't change, nothing changed. For the other part, we had this, so basically we have minus 1 over 3, that's a constant, we keep it in front, and this looks like our fetish series where x is replaced by x over 3. So my fetish series, so I have my minus 1 over 3 so I don't forget, my fetish series, so minus 1 over 3 times my series, and then I will need to replace here, instead of x, x over 3. I replace it here, so I'll have x over 3, so this is equal to my expression. I replace it as a general term, so instead of x is x over 3, and I replace it in the expression of the interval of convergence. Instead of x is negative, in this case is x over 3. Okay, it doesn't change much, but okay. So I will have at the end x over 3 in absolute value smaller than 1, so x in absolute value needs to be smaller than 3. So what we realized is that when we rewrite it, our interval of convergence is a little bit different. That's fine, there's nothing wrong with it, it's okay. So basically we have this. Now what we could do, since we multiply every term by 3, 1 over 3, so the 3 downstairs, well, we could move it here, so we have 3 to power n plus 1. So essentially this simplifies a little bit the writing. So those are the two pieces that I have from my expression, and I have the two series. So now it's a little bit of a struggle. One series, so this one is convergent on interval negative 1, 1, and this one is convergent on interval negative 3, 3. So if I want to add them, because this boy here, it lives only on negative 1, 1. So outside that interval, it's not convergent at all. So you can say the series is not convergent, so it's equal to nothing. So basically, in order for this function to be equal to a series, we need to say, okay, since this series is convergent on a smaller interval, the entire summation will be convergent only on a smaller interval. So we essentially have intersection of intervals of convergence, right? So what we do, we see both series start at 0, which is good, and they have x to power n, x to power n, so I can factor x to power n. So in the first case I'll have negative 1, and the second case I'll have negative 1 divided by 3 to power n plus 1. So that's how I got this expression. I just factored xn. Okay, so I have a series of this, and this series is convergent on the interval negative 1, 1. So it's intersection of the two intervals of convergence. So essentially the smaller one is the one that we keep. But in general it would be intersection. So this example was a little bit more complicated, which was we had two different series, we had to add them, they had different intervals of convergence, so it was a little bit more involved. This is a similar example with the partial fraction, so I'll skip it. It's the same procedure. In this situation here, if I want to represent this function by a power series using my fetish series summation of xn from 0 to infinity, which is a geometric series, what I realize is that this looks like a derivative of something, like derivative of 1 over x1 plus x. Now obviously if I differentiate 1 over 1 plus x, it will be negative this expression. So if I move the negative on the other side, this is what I get. So basically my function is equal to minus the derivative of this expression. You can compute it just to make sure, obviously. So that means in order to get this function as a power series, all I need to do is have minus 1 times the derivative of the power series for this expression. So the power series for the expression here is the alternating version of our fetish series, and now all I need to do is differentiate it term by term, right? So my function that was given to me is equal to minus derivative of this thing here, which is equal to minus derivative of the power series term by term. So only x's are differentiated. So obviously x goes down, so I'll have n x to power n minus 1, and the starting point will not be 1, it will be, it will not be 0, it will be 1. So when I differentiate, I get 1. You could write it out just to see, obviously, it doesn't hurt, but by now we know what's going to happen. So I have minus 1 times my series that I got with differentiation. Now this is minus 1 times every term, so basically what happens is that the signs flip. So I have minus 1 times minus 1 to power n, so it's minus 1 to power n plus 1. That's why I rewrote it, just to have a more compact expression. Obviously, in this situation, we didn't change any x, right? We didn't replace x by anything, so the interval of convergence stays the same. By the way, if you want to check just for fun what's happening at the end points, if you plug 1 here, you'll have alternating series of n, which is divergent because general term doesn't go to 0. And if you replace it by minus 1, again you get a different sign with n. Again, general term doesn't go to 0. By divergence test is divergent. So really the interval of convergence, interval on which these two things are equal, is open negative 1, 1. Just to push the things further, if I want to have here the power 3, obviously what we will do, we will take this, differentiate it in see what we get. So if I differentiate 1 over 1 plus x squared, so I'll have minus 2, right? And then minus 2 times this. So basically I move minus 2 to the other side, I divide by it, so this is what I get. Or adjust the constant as you wish. So basically my function is minus 1 over 2 times the derivative of this thing. This was already computed, so we again we differentiate the expression. So what happens when you differentiate? N minus 1 goes down, and then we have n minus 2 as a power, and then we start at 2, obviously. So this is automatic, you don't need to think too much. If you wish, you can write it out a little bit, but I think it's not necessary. You know, you differentiate this piece with respect to x, n minus 1 goes down, and the power of x becomes n minus 2, and the starting point will be n from 2. This is just to push the things further. Now we can multiply that thing by x squared and get another expression. So basically we take the series that we just got and we multiply it by x squared. So we multiply each piece by x squared. So basically we are increasing the power of x. So it's going to be x to power n plus 2 times x squared. So it is x to power n minus 2 plus 2. So x to power n here. So this is just to show you a little bit that we can have complicated expressions. We just write it piece by piece, and that's it. It's not more it's not really more difficult. It's just longer. I think we already saw the ln. So basically, what we do, we differentiate. We realize what's the derivative. If we integrate the derivative, we get our ln. So this is minus 1 times our fetish series, and then I integrated. Obviously I'll get the constant of integration, which I need to fix. So again, we choose wisely the value of x, because this is equal to each other for any value of x between -1 and 1. So we choose something wisely. So 0 seems a wise choice, simple one. So that's how we get the expression here. And again, we need to check what's happening at the end points. At x equal 1, what happens is that the function is not defined, therefore we cannot be equal. And at x equal minus 1, well, the function will be ln2, and we will have negative 1 to power n divided by n. So this is alternating harmonic series, which is convergent. We know it already by alternating series test. So in this situation, the radius is still the same, but in the interval of convergence, or for the equality, minus 1 also is okay. So any value between -1 and 1, including -1, but excluding 1, because we saw that at 1 the function is not defined. So this is just a cute thing. If I evaluate this expression at 1 over 2, what happens? 1 minus 1 over 2 is 1 over 2. 1 over 2 is 2 to power minus 1, right? So it's just rewriting a little bit, it's cute. So if I plug here, instead of x, 1 over 2, this is what I get. So basically this is just for fun, finding ln2 is equal to this series here. Nothing special. Again, we can always complicate things by multiplying the series that we got by another power of x. So this is usual. If we had this to do from the beginning, we would do the first part is to find the expression for the ln, and then to finish we would multiply by x. Here, okay, this one is a little bit different. So again, the x is not an issue. We will multiply by x the result that we get. It's not a problem. Here we have square, so that means this comes from the differentiation of 1 plus x4 downstairs. So if I differentiate 1 over 1 plus x4, I'll get negative 4 upstairs, so that's why I divide by negative 4 both sides, so that way I get the proper expression. You can, by the way, differentiate this and realize that the derivative is 1 over 1 plus 4x squared. Now x is multiplying all of that, so that's not a problem. I just write x times the derivative. So now this part here, it's very similar to my fetish series. So I have the alternating version of it where x is replaced by 4x, or if you go for the original, you replace x by negative 4x. And you replace it everywhere, obviously, even in the interval of convergence. This is super important. We need to do it. So there's nothing special here. We differentiate xn, so n goes down, and x to power n, 1 and minus 1, and summation starts from 1. So basically, that's what's happening. Nothing special here. At the end, we multiply x inside, because x doesn't depend on n, so we can multiply each term. So that means the power of x will be x n minus 1 times x, so x n minus 1 plus 1, so x to power n. This way it just looks nicer. It's better to write it this way. This is very similar situation. We are getting used to realizing when we have something here with square that becomes this comes from the differentiation, so it's important. So we recognize that, then we are able to rewrite it. So this is our fetish series. We differentiate this. Okay, fine, we get our series. And now we need to multiply it by 1 plus x. Obviously we split it in two pieces, so we have summation of two series actually. So you see one and the other, and then the other one with x times, so here the power will be n. So here what is interesting, both series start at the same value of n, however the powers are not the same. So this will be a little bit of a struggle to write the combined series with the correct power here. So that will be a struggle essentially. So what we do, we take the first term and we see what we can do here. So if I start from n equal 1, I have 1 x to power 0, so it's 1, plus the series from 2 onwards. Now this will be 2 to power times x to power 1, then 3 x to power 2. So I realize what's happening. The constant here is 1 bigger than the power. Obviously, we see it from here. So basically I can rewrite it this way. So now both series start at 1 and they have x to power n. So now I can actually regroup it this way. So I have my 1 plus the piece. So these two series, they start at 1, both of them, and they have x to power n. So I can factor x to power n. So I'll have n plus 1 plus n, so that's 2n plus 1, factor of x to power n. So this is important to rewrite just to have a nice expression. So basically we can realize here that this thing is equal to here if we just start from 0. So this was a little bit more involved, true, but it's important just to see what to do, that we are actually able to solve these problems, even though they look a little bit complicated. So log of a ratio is difference of logs, so the similar procedure. I'll skip this. Here what's interesting is that we have an expression and we need to integrate it. So again, we start from the beginning. We know our fetish series, so we will replace x by negative x to power 3. So we get this expression. So again, the interval here is negative x to power 3 smaller than 1. So again, x is between negative 1 and 1. And then we need to multiply by x. Okay, fine. So the power on x will increase by 1. And now we integrate this. When we integrate, we will have constant of integration, obviously. So this is just sequential process, step by step. Even though it looks a little bit scary, just go step by step. So basically we now integrate term by term as we are supposed to, because these are power series. When we integrate, we have a constant of integration, and I write it in front so I don't forget. Integral here, 3n plus 1, so 3n plus 2 divided by 3n plus 2, obviously, so there is nothing special. Now we need to find the constant. Oh, no, here we have the integral. Okay, it's fine. There's nothing particular here. What we could see is the interval here, minus 1, 1, and then we can ask ourselves, okay, what happens at the end points? Do we have equality at the end points? So at minus 1, here we would have division by 0, so this integral would not be defined. So at minus 1, obviously, they are not equal because one term is not defined, so bye-bye. At x equal 1, what happens? Well, this term, if I plug 1, I had 1 over 1 plus 1, so 1 over 2. If I integrate, I get x over 2 plus some constant, so that's okay. There's nothing wrong with there. And if I plug 1 in the series here, I'll have an alternating series 1 over 3n plus 2, which by alternating series test is convergent. So basically I would have something that makes sense on the left side and something that makes sense on the right side. I have convergent series and I have some expression here. So that would mean that at x equal 1 we have some type of equality. So basically our interval convergence is open minus 1 and closed 1. This example is very interesting. So basically we have this expression that we had, but with the bounds. So we need to estimate the value of the integral between 0 and 0.3. And we want approximation with 6 decimal places. We will see what this means. So we already know that we have an alternating series. Now, this is from the previous slide, so basically we know that this is equal to this series here with the C. So basically, what do we do? So integral is here and it needs to be evaluated between 0 and 0.3. So essentially the antiderivative is here and we evaluate it between 0 and 0.3. How do we do that? Well, normally we take this part, evaluated 0.3 instead of x, minus, again, this part with x equals 0. So we'll have c minus c, so it's going to be 0. And then we have this part here with x equal 0.3, minus the same thing with x equals 0. So I have 0 to power here 2, that's the first term, and after that everything else is 0 also. So this simplifies a little bit. Right, so we have our antiderivative that is evaluated at the bounds. So the upper bound, we plug it. The lower bound, if you plug 0, everything is 0, right? So there's nothing special there. So now this definite integral is equal to this series here. Now they want an approximation, so we need to add certain number of these terms to get an approximation, and they want an approximation with 6 decimal places, which means we need as error something that has 6 zeros at least. So we check each of these expressions, we see that this is an alternating series, and we remember immediately, oh, the error of alternating series is the next neglected term. So we evaluate each term and see which term is the first one to have 6 zeros. So the first guy that has 6 zeros is this term here. So this means that this term represents our error, and these terms here will be used to get an approximation. Why? Because this is an alternating series and error on alternating series is the first neglected term. Here we want to have that term to have at least 6 zeros, while this one has. So that's the reasoning process here. I have an alternating series. How many terms do I need to add? Well, as many as I hit the first term that has 6 zeros here, because they want 6 decimal places. It turns out to be this term here. That's my error representation. So this is bigger than my error. So I make sure that I'm getting my 6 decimals. So that means that the previous terms are used to approximate. Okay, this is also, it looks a little bit complicated. So it's x to power 3, 2 minus x to power 3. So now x to power 3 will be multiplying the result. Here we have 1 over 2 minus x to power 3. That means there was a couple of derivatives here involved. So if we have this part and then we rewrite it properly. Now if I differentiate this, I get here with the square. So I differentiate the left side. N goes down. We start from n equal 1. And if I differentiate this, I'll see what I get. I'll need to differentiate this part also. Right? So if I differentiate this part, I'll have 2 upstairs, so I divide by 2 also. So this term is equal to 1 over 2 times the derivative. So we differentiate. N minus 1 goes down also. Power is n minus 2. We start from 2. So nothing special. Here I had 2 downstairs and 2 downstairs. So I have 2n plus 2. So that's why we have this here. Now the last step is to multiply by x cubed, everything. So I multiply by x cubed. So this will be x cubed times this expression with x. So the power will be x to power n minus 2 plus 3. So n plus 1 is the power. Okay, so we can keep it here, or we can rewrite from 0. It's up to us. Doesn't matter really. So these are similar procedures, so I'll skip it. Here is one that is interesting because the constant of integration is not 0. So if I want to have a representation of this function, ln 5 minus x, in terms of power series, well, first thing is to remember that we have our fetish series and we need to write things in terms of the fetish series to start with. So now if I differentiate this thing, I'll get 1 over 5 minus x times minus 1, right? And then so if I integrate that part, I'll get ln. So basically I differentiate and then I know that the integral is equal to this. Now if I look at this term here, this is close to my fetish series. Okay, I have 5 instead of 1, so I'll factor 5. So I have 5. Now I replace in my fetish series x by x over 5. So I get the expression, nothing special. And now I need to integrate that expression. Right? The minus I don't forget. And I integrate it, so minus. And the integral is term by term because this is a power series. So n plus 1 over n plus 1, right? So that's it. We don't forget the constant of integration. Note here, we replaced x by x over 5, so we had absolute value of x over 5 smaller than 1, so absolute value of x is smaller than 5. Right, that's where it comes from. Now we need to find the value of c. What I did here is just rewrite a little bit, because if I start at 0, I get here 1 and then x to power 1, 5 to power 1. So if I start from 1, I can simplify the writing of the series. You don't have to, but I did it just to have something cute. So now I need to find value of c. So this equality holds for any value of x between negative 5 and 5. And again, the wise choice is 0 because it's easy to evaluate left side and right side. The problem is always to evaluate the series, so that's why we choose something that will simplify the computation of the series. So if I plug 0, everything is 0 here, so the series is 0. Now I will have ln of 5 equals c. So you see, if I plug 0 everywhere, I'll have c, okay, here. And then when I plug 0 here, I have 0 to power 1 plus 0 to power 2 plus 0 to power 3, right? Everything 0, this division by number, so it's everything is 0. So this series is equal to 0. On left side I have ln 5 minus 0, so ln 5 equal to c minus 0. So in this case, c, the constant, actually is equal to ln 5. So my function ln 5 minus x is equal to ln 5 minus my series. And the interval is here. Now, let's see what's happening at the end points. Maybe one of them or both are included or not. So first thing is to realize what's happening at x equal 5. At x equal 5, I have ln 0, so that's not defined. Therefore, at x equal 5, the function is not defined, so the equality cannot hold. Okay, fine. So x equal 5 is not in the interval. That's cool. X equal minus 5. If I plug minus 5, I'll have 5 minus minus, so this will be 5 plus 5, so ln 10. So that's a number that exists. Here, if I plug minus 5 instead of x, I'll have minus 1 to power n, 5 to power n, so 5 to power n will simplify. So I'll have minus 1 to power n divided by n. That's an alternating harmonic series, so we know it's convergent. So I'll have ln 5 minus an alternating convergent series. We know that the value here is ln 2, but doesn't matter. It just matters that it's convergent. So I have the function is ln 10, and then here I have ln 5 and I have a convergent series. So that means that at x equal negative 5, the function is defined, it's cool, and the series is convergent also. Therefore, the equality holds also at minus 5. So the interval for which my function is equal, so this thing here is equal, starts from negative 5, including negative 5, up to 5, but excluding 5. So that's just interesting to observe. In this situation, in this case, our constant was not 0, because usually we had 0, 0. So some people might think that it's always 0, but it's not. We need to really compute. In this situation, it was ln 5. So this is another complex case, in the sense that there are several pieces. We will multiply the things by x squared towards the end, so there's no point focusing on that. Tan inverse of x cubed. Wow. Well, if I compute the derivative of this, what do I get? The derivative of tan inverse x cubed is 1 over 1 plus square of the argument, so x cubed squared, so x6, times derivative of the argument, which is 3x squared. Cool. So now if I integrate this, I'll get tan inverse of x cubed, obviously. So why is this interesting? Well, I have 1 divided by 1 plus x to power 6. So this is similar to my fetish series, so I'm able to do something. So right, this is equal to this. So in my fetish series, I replace x by negative x to power 6, essentially. And then I multiply this expression by 3x squared. So the powers on x increase. Now the next step is integrating this. I'll get tan inverse x cubed. Okay, so I integrate this term by term. Obviously I have my constant of integration that I need to fix. Integrating term by term. So here plus 1 divided, so 6n plus 3 divided by 6n plus 3. So here we can factor 3, it will simplify here, so we'll have 2n plus 1, so that's what happens. Finding the value of c, again here the wise choice for x is 0, so it simplifies. I'll have 0 on one side equal to c plus, and this series will be series of zeros, so that's fine. So this is what we get. Now the final step is multiplying this expression by x squared. So x squared times this piece here. So x squared times this. So the power on x will increase to 6n plus 5. So there is nothing special there. Now the last piece is to see if the equality holds also for the endpoints. If I plug 1, I'll have an alternating series, 1 over 2n plus 1. It's easy to verify by alternating series test that this is convergent. And if I plug minus 1, again I'll get an alternating series with the same expression, so it is also convergent. So in this situation, both endpoints are valid. The function itself is valid in those values, and the series is convergent. So we can say that this equality holds for all values of x between -1 and 1, inclusive of -1 and inclusive of 1. Okay, let me see if we have something different. This is similar with these derivatives. So it's just important to realize when you differentiate ln to differentiate properly, and then you realize, okay, here I can replace x by negative x to power 4, and then we go. These are just cases that look more complicated. It is only to show you the complexity, but actually we decompose everything piece by piece. Maybe this example here where we estimate again the value of the integral, approximation to 6 decimal places, and we suspect that this will give rise to our alternating series, because then things will be easy, because we have the estimate of the error being the term that is neglected. So here again we can find the series for this part and multiply it by x squared. Again, here x is replaced by negative x to power 4, so we see it directly, so there's nothing special there. And then we multiply by x squared, so the power of x will increase, 4n plus 2. So that's our integrand. Now we integrate this. How do we integrate? Term by term as usual, because this is a power series. So 4n plus 3 over 4n plus 3, constant of integration. For this this example we don't need to find it, because we will evaluate the integral, so this is definite integral, so the constant will be eliminated anyways. So now this is the integral, so this is the antiderivative actually. So we evaluated at 0.3 and 0. And you see the choice of 0 is fortunate, because it simplifies our life. If we took, I don't know, 0.1, I would need to evaluate the series with 0.1 here, and that would be very complicated. So that's why most of the time one of the bounds is 0, because it simplifies our life. So at the end it's just the series evaluated at the top bound. So that's what we have as an expression. I just wrote a couple of terms. Now what they want is an approximation that is correct to 6 decimal places. So first observation, this is an alternating series. That's good. And we know for the alternating series that the error term is smaller than the first neglected term here. So we need to evaluate each of these pieces and see which one is the first one to have 6 zeros. in its expression. So once we do that, we realize that already the third term is something like this. So this one has 6 zeros in its expression. So since my error needs to be smaller than a term with 6 zeros, so this is my estimate for the error. So this is my estimate for the error, and the estimate for the sum is everything in front. So I use these two expressions to find the approximation for the integral, and I know that this is correct for 6 decimal places because the next term here has 6 zeros. This is another one similar. Maybe no need to go to the procedure. What matters is, again, conveniently we started 0 to 0.5, so one of the parts will be 0. So again, here they want 6 decimals, so that means I want an expression with 6 zeros. So this one will not give me, it's this one that will give me 6 zeros. We can evaluate it in a calculator, obviously. So the error is this term, and everything in front is used to estimate the value of the sum, which is here estimating the value of the definite integral. So those are some examples of applications. Some of them are straightforward, some of them require some differentiation or rewriting a little bit, but this requires a little bit of practice. It's not scary, just requires practice to have a strategy of the procedure. So please solve some of these examples to make sure that things are clear in your head to have a strategy to solve.